Good morning, children. Sairam and welcome back. Children, in the previous session, we have learned about the developments that led to the development of a quantum mechanical model of atom. I have told you there are two important developments because of which this quantum mechanical model was developed. The first one was dual nature of matter, as the electromagnetic radiations show dual nature, that is particle like nature and wave like nature. Similarly, all matter particles which are there in motion, they also exhibit dual nature, that is your wave nature and particle nature. Now today we'll be studying about the quantum mechanical model. Now before that, the second development that led to the development of this quantum mechanical model was the Heisenberg uncertainty principle. That is, impossible to measure simultaneously both the position and momentum of microscopic particles with absolute accuracy. Now today we are starting with a quantum mechanical model. Before that, you should be knowing what is the meaning of the word quantum. As we have learned in Planck's quantum theory of radiation that according to Planck quantum theory of radiation, we have learned that the electromagnetic radiations or any radiation, they travel discontinuously in the form of small packets of energy, and these packets of energy are called quanta. So we are talking about what? The quantization of energy, that means in the form of small packets. Now what is quantum mechanics? It is that branch of science that takes into account the dual behavior of matter, and it is called the quantum mechanics. In dual behavior, you all know that is the wave-like behavior and the particle-like behavior. Now, see children, this dual behavior is just a theoretical concept, and it deals with the study of motion of microscopic objects that have both wave-like and particle-like properties. Now, this we cannot apply to the macroscopic objects, as I have told you earlier. Why? Because for macroscopic particles, the Heisenberg uncertainty principle does not hold true. Why? Because for macroscopic, macro means big. For macroscopic particles, the mass of that substance will be so high that the wavelength will be very low. That means it will be of no use. Now, we'll study about the important features of the quantum mechanics today. Actually, you're not concerned with the important features. The important part for you is the quantum numbers. These features of quantum mechanics are not actually in your syllabus, but you should be knowing, because without knowing these features, you cannot understand the quantum mechanics. Now see, the first important feature of quantum mechanical model is that the energy of electron in atom is quantized. Quantized means it has a particular amount of energy. As de Broglie have also explained, only those orbitals are permitted which have the energy equal to h upon 4 pi. Angular momentum equal to that. Similarly, here also in quantum mechanics, it has been explained that the energy of electron is quantized. That means we cannot say electron in an atom can have any amount of energy. No, it is not like that. It will be having a quantized amount of energy, and the other electrons will have a multiple of that quantized amount of energy. We can also say that the energy of electron in an atom is quantized, that is, can have only a specific value. For example, electron are bonded to the nucleus in atom. So, because of this, the electrons are bonded to the nucleus. That means the nucleus is attracting, but not the electron at every place. The electron and suppose this is the nucleus, this is the electron. Electron is having a quantized amount of energy. It can exist here or here. It cannot exist here. And because of this quantization, the electron is not going inside the nucleus even though the attraction is there. Now, the second important point of quantum mechanics is the existence of quantized electronic energy is a direct result of wave-like properties of electron and are allowed solutions of Schrödinger wave equation. See children, Schrödinger and Heisenberg, they gave a wave equation that told about the energy of the electron in the orbital, you can say, and will not be talking here about the orbits, will be talking about the orbitals only, and will not be talking about the position of electron, will be talking about the probability of finding electron. Probability means the more chances are there of finding electron. And Schrödinger, he gave one equation that was actually telling about the psi. And what is psi? Psi is a probability of finding electron. It is denoted by the sign psi. This is probability density. Now, the path of an electron in an atom can therefore never be determined. That means we cannot determine the path of the electron. So what we talk about is, we talk about the probability of finding electron at different positions in an atom. So children, as I told you that it is not possible to find out the position of electron. We can only talk about the probability of electron in an atom. Number 4 is an atomic orbital is the wave function psi for an electron in an atom. What is meant by an atomic orbital? It is the wave function psi. Psi is given by Schrödinger and he tells about the probability of electron. The Schrödinger wave equation is not there in your syllabus. You have to just remember this quantization energy is also not there. These quantum mechanics principle, only the quantum numbers are there in your syllabus. So you have to just remember these things. But if you will not be knowing this thing, you will not be able to understand the concept of quantum numbers. Now next is the probability of finding an electron in an atom at a point is proportional to the square of orbital wave function. This orbital wave function is psi and its square will tell you about the probability of finding electron, or you can say the probability density. So it is known as orbital wave function. Psi square is the probability density, or you can say the orbital wave function. Now children, on the basis of this, the important part that comes is the quantum numbers. Now what are quantum numbers? You can simply say they tell you about the address of electrons, the place where the probability of finding electrons is maximum. Now these quantum numbers are quite tough to explain in the form of slides. Still I'll try. You also have to be very careful while understanding the quantum numbers. Now see, there are 4 quantum numbers. The principal quantum number, Azumithal quantum number, magnetic quantum number and spin quantum number. Principal quantum number is denoted by small n. Azumithal quantum number is denoted by small l. The magnetic quantum number is denoted by small m and a small s in the subscript. Principal quantum number by small n, Azumithal quantum number by small l. The magnetic quantum number, it is denoted by small m and a small l in the subscript. And the fourth one, that is the spin quantum number, it is denoted by again small m but a small s in the subscript. These are how the quantum numbers are denoted. Now what are quantum numbers telling? They are telling you about the address of electron. Now if I say if we are talking about the principal quantum number, the values of principal quantum number n will be either equal to 1 or 2 or 3. It will tell you about the shell. So what principal quantum number will tell you? It determines the size to a large and the energy of the orbital. It also tells you or also identifies the shell. With the increase in the value of n, the number of allowed orbitals also increase and are given by n square. All the orbitals in the given value of n constitute a single shell of atom. So, n will be equal to 1, 2, 3 or it can be 4 also. Now, what is the meaning of 1? Means the K shell. You've learned about this concept in 10th standard. KLMN shell. K, L, M and N. So, principal quantum number 1 corresponds to K. 2 corresponds to L. 3 corresponds to M. And 4 corresponds to N. So, what principal quantum number will tell you about the shell in which the probability of finding electron is there. Now, second is the azimuthal quantum number. It is also known as orbital angular momentum or subsidiary quantum number. It defines the three-dimensional space of orbitals. Now, for a given value of n, the value of L will be like, suppose the value of principal quantum number is 1. Then the value of azimuthal quantum number will be equal to n minus 1. That is equals to 0. Similarly, if the value of principal quantum number n is equals to 2, then the value of L will be equal to up to n minus 1. It is up to n minus 1. It will be equal to 0 and 1. Now see, if any value of L you are having, like you are having L is equals to 0, 1, 2 and 3. These are the possible values of L. 0 you have to remember. Just remember this. I will explain you the meaning later on. It is S. 0 corresponds to S. 1 corresponds to P. 2 corresponds to D. Small d. Okay. And 3 corresponds to small f. It is S, P, D and F concept that is actually telling you about the orbital angular momentum. Now, you can also say that each shell consists of one or more subshells or sublevels. The number of subshells in a principal shell is equal to the value of n. For example, for this first shell, n is equals to 1. There is only one subshell, that is L is equals to 0. If the value of n is 1, L will be equal to 0 only. That means only one subshell is there, that is S. If the value of n is 2, then two subshells are there, 0 and 1, that is S and P. So what is azimuthal quantum number telling you actually? About the subshells. Now, next is the magnetic quantum number. Children will be discussing this magnetic quantum number and spin quantum number in the next presentation. Till then, you go through properly with this quantum mechanical model of atom. Read about the Schrödinger wave equation and the Heisenberg uncertainty principle also. See, though it is not there in your syllabus, but you should go through it. Then only you will be able to understand the next concept. Okay, thank you. Sai Ram.